Welcome back. We're in our linear programming session. If you remember, we're just doing the graphical method in this section. So example 2, find the maximum and minimum values of c equals 2x plus 3y. So again, this is our objective function. Subject to these 5 inequalities, these are called our constraints. We have x plus 2y is less than or equal 48, x plus y is less than or equal 30, 2x plus y is less than or equal 50, x greater than or equal 0, y greater than or equal 0. Let's see. I think I'm going to go to 40 on the x and y axis this time. If you can't see that right away, don't forget you can do the cover-up method. So for this first line, if I cover up y, I get x is 48, 0. Nope, that already tells me I did it wrong. Let's go to 60 then. And then if I cover up x, I need to divide by that 2, so we get 0.24. If I cover up y, we get 30. If I cover up x, we also get 30. If I cover up y, I divide by 2 to get 25. If I cover up x, I get 50. So I'm glad I decided to go to 60. Now x greater than or equals 0 is our vertical line. Y greater than or equals 0 is our horizontal line. Again, these two are just telling us we're in the first quadrant. Well, now 48, 0 is right there. 0.24 is right there. And connect to them. Then we got 30, 0 and 0.30. And connect them. And then 25, 0. So 15, 18, 21, 24, which is just a little bit past 24. And 0, 45, 48, 51. So a little under 51. So again, we have 1, 2, 3, 4, 5, 6, 7 regions to check. I am just going to start with this, which is 3, 3. Is 3 plus 2 times 3 less than or equal to 48? I think that's pretty obvious. Is 3 plus 3 less than or equal to 30? Yep, again. And then is 2 times 3 plus 3 less than or equal to 50? Yes, it is. And again, these two, 3 is greater than or equal to 0, 3 is greater than or equal to 0. It does check out, but I don't need it. So we have this region as our feasible region. Now remember, our objective function is hovering over this like a table, and we need to figure out where does this table have the highest point. It must occur at one of the vertices. So we have this vertice right there, which is 0, 0. We have this vertice right there, which was 0.4. We also have this vertice down here, which was 25, 0. And then we have these two vertices, which I do not know what they are. So we need to do some extra work. So actually, let me do those in different colors. Let's do orange for that one. Now that came from the one with the smallest y-intercept, which is that one, and the second smallest y-intercept, which is that one. So I need to solve this system of equations now, x plus 2y. is equal to 48, and x plus y is equal to 30. I hope you see if we just subtract them, we get y is equal to 18. Plug it back into the second equation. We get x plus 18 is equal to 30. Subtract 18 from both sides, and we get x is equal to 12. So that orange point is the point 12, 18. And now we have this point right here, which is the second smallest y-intercept and the largest y-intercept. So we have 2x plus y is equal to 50, and x plus y is equal to 30. And again, I need to solve this system of equations. I'm going to subtract them. We get x is equal to 20. Plug into the second equation. 20 plus y is equal to 30. Subtract 20 from both sides. Get y equal to 10. So that blue point is 20, 10. So now that I have found all my corner points, I need to figure out which one is actually the minimum. Oh, we want maximum and minimum. So I plug them in. So we get 2 times 0 plus 3 times 0, which is 0. If I was a betting man, I'd say that's our minimum. Then we get 2 times 0 plus 3 times 24, which is 72. Then we get 2 times 25 plus 3 times 0, which is 50. 2 times 12 plus 3 times 18. What does that come out to be? $78. And then 2 times 20 plus 3 times 10, which is 70. So our maximum is there, and our minimum is there. How would we write that as our answer? I'll do it right here. There is a minimum of 0 at 0, 0. There is a maximum of 78 at 1218. So that's how these linear programming problems work. Notice how they are quite involved and there are multiple steps. First, you have to graph inequalities, you have to solve systems of equations, and then you have to plug points in. So example 3, find the maximum and minimum values of c equals x plus y subject to these constraints. So again, the c equals x plus y is called our objective function. And these inequalities over here are called our constraints. X greater than or equal to 0, y greater than or equal to 0 tells us that we're in the first quadrant. I'm going to do the cover-up method here. We get 4, 0 for the x-intercept, 0, 6 for the y-intercept. Get 11, 0 for the x-intercept, and 0, 11 thirds for the y-intercept. I'm just going to go 20, 20. So 4006 is right there, and then 11, 0, 0, 11 thirds. 12 thirds would be 4, so it's just a little bit less than that. Okay, now I need to figure out shading, so I'll plug 1, 1 in. Is 3 plus 2 greater than or equal to 12? Nope. Okay. So that didn't work. I need to pick another one out. Let's go 5, 5. So 3 times 5 is 15, plus 10 is that greater than or equal to 12? Yep. And then it's 5 plus 15 greater than or equal to 11? Yes, it is. So we get this. Oh no, it's not bounded anymore. So this time we're not guaranteed to have a solution. So we still need to find the corner points though. That corner point isn't too bad. That's 0, 6. This one's 11, 0. And then this one, we need to solve a system of equations. It's probably going to end up being 2, 3 though. But I'm still going to solve the system of equations. Since there are only 2 equations here, it's pretty easy to figure out which 2 we have to combine. But it is 3x plus 2y is equal to 12. And x plus 3y is equal to 11. Multiply this bottom one by negative 3. So then we get, the top doesn't change. Negative 3x minus 9y is equal to negative 33. Which is negative 7y equals 21. Negative 21. Divide by negative 7, divide by negative 7, y equals 3. And then x plus 3 times 3 equals 11. X plus 9 equals 11. Subtract 9. X equals 2. So I was correct, as in 2, 3 is that point. We plug them into the objective function. So 0 plus 6 is 6. 11 plus 0 is 11. 2 plus 3 is 5. So you might be tempted to say that 11 is our maximum and 5 is our minimum. But we really don't know if that's true or not. So what we have to do is pick another test point in our unbounded region as far away as possible. So 20, 20 is pretty good. So if I do 20, 20, that would become 20 plus 20, which is 40. So what that's telling me is that this is going up forever. So there is no maximum. There is a minimum. Of 5 at 2, 3 still though. So, let me go up so you can see it. And that's examples of doing some linear programming.